Okay, so today we are going to talk about discrete random variables. We will briefly mention continuous random variables. However, we kind of have to remember the placement of this unit. It usually comes before our inferences. And with that being said, the AP stats exam really only focuses on continuous random variables in the realm of inference testing. So we've kind of already done that. So we're just going to focus in on discrete today. So we're going to start with an example. Suppose that we toss a coin 3 times. So the first thing we always kind of want to consider is what is our sample space? What are the possible outcomes for this scenario? So I went ahead and labeled all 8 possible outcomes. The way that I approach this is I generally start with what's the possibility of getting all heads, and then I kind of change one as I go along. I do the same thing with tails, change one as I go along. And then basically you kind of generate all possible combinations. So the total number of outcomes is 8, and the probability of any one outcome is 1 out of 8. So I have my sample space, and typically we denote sample space with the capital S. I have my number of outcomes, I have the probability of any outcome. So now we are going to define event X as the number of heads out of 3 coin tosses. So this is kind of setting us up to create a probability distribution. Notice I have my symbols, meaning where X is going to be equal to 0, which means no heads in 3 tosses. X is going to equal to 1, which means 1 head in 3 tosses. X is going to equal to 2, 2 heads, 3, 3 heads. So now we're going to define that probability by going in and saying, well, the probability of me getting no heads in 3 tosses is that event tails, tails, tails. So that's one outcome, 1 out of 8. Probability of 1 head in 3 tosses, I can go in and see 1 head, 1 head, 1 head, 3 outcomes, 3 out of 8. And for 2 heads, that is also 3 outcomes, 1, 2, 3. And then 3 heads and 3 tosses, that's our one event, heads, heads, heads. So I get one outcome, 1 out of 8. So we have generated the total amount of possible outcomes, meaning I could either get 0, 1, 2, or 3. There's no way I'm getting 4 heads. There's no way I'm getting -1 head. It's 0, 1, 2, or 3. Can't be in between. It can't be half. It can't be a quarter. 0, 1, 2, 3. And then we've generated the probabilities for each of those events. So now what I'll do is I'll organize this into a table, and we call this table the probability distribution. So in the top, we call it X, and we're going to put in all of our possible outcomes. So 0, 1, 2, and 3. And in the next row, generally it is a row like table, I'm going to put in all my probabilities of X. 1/8, 3/8, 3/8, 1/8. Now, if this were to appear on the AP exam, which it does more often than not, it's a simple question. They just want you to list all the possible outcomes and their given probabilities. It's an easy FRQ question that they like to throw in there to get you started, get the ball rolling. Not something you want to focus and like think about too much. It is as easy as it seems. So now what we're going to get into is how to identify probabilities of specific instances. So, what is the probability of me getting X is equal to 2? Well, that one's pretty easy. All I have to do is go to my table, go where it says 2, and that is 3/8. Then we want to find the probability that X is less than 2. Well, if it's less than 2, the only options I have is it's either 0 or it's 1. So I'm going to take the probability of X is equal to 0 and add it to the probability of X is equal to 1. So that's going to give me 1/8 plus 3/8 equals 4/8, which is 1/2. And with discrete random variables, paying attention to whether you are including the value with an equal sign is very, very important because it does change your possible probabilities. So, probability that x is greater than or equal to 2. So I can say that it's equal to 2, and what's the probability that it's greater than that? So I'm considering 2 and 3. So I'm going to get probability of x is equal to 2 plus probability of x is equal to 3. So I'm going to do 3 eighths again plus 1 eighth, going to give me 4 eighths, which is 1/2. Now, when you're dealing with probability distributions, you most likely will be dealing with a table. However, there are instances where they present this information to you via a histogram. So I went ahead and drew one up for this specific situation. Generally, you will have your x, your outcomes on the x-axis, and you will have the probabilities on the y-axis. I have 0, 1, 2, 3, and we consider this a histogram just because there is no in between values that we necessarily can obtain. I can't get 1.5 heads. So 1 is going to represent that only, that's the only possibility of it happening. So I have 1/8, 3/8, 3/8, 1/8. Now again, generally they're going to give you a table, but they might switch it up and give you a histogram. It is read in almost exactly the same way. You'll have your outcomes, you'll have your probabilities. And again, you always want to verify that it is a legitimate model because they may try to slip that in there to trick you. Make sure it adds up to 1, make sure all of your probabilities are between 0 and 1, and you are good to go. So, this is kind of just the intro to probability distributions. Now, let's kind of define some things. So, what is a random variable? Basically, a random variable just takes on numerical values that describe the outcome of some chance process. Again, we are working with randomness. Probability is built on long term what's going to happen. And random variables are usually represented by capital letters. That's why in the previous example, you saw me use a capital X. It's just what they like to do. When we were doing Venn diagrams, we were using capital A's and B's. It's just the easiest way to kind of differentiate between a normal variable and a probability variable. And random variables can be discrete or continuous. And like I said earlier, we are focusing in on discrete today, not necessarily continuous random variables. And they are something that has to be numeric in value. I can't have my random variable is cat and dog. Not going to work. It has to be a numeric outcome that I am getting. Now, discrete random variables, we did talk about this briefly early on in our survey taking in unit 3 and unit 2. A discrete random variable has a fixed set of possible values, meaning we have the outcomes and we know that this is what is occurring. And typically, there's no decimals, and sometimes it does not include every number. Now, the one exception with decimals, I would say, is potentially shoe size. Generally, we consider shoe size to be discrete because it is a fixed set of possible values. You're a 7, a 7.5, an 8, an 8.5. You can't be a 7.95. So it is still fixed. It's just that's one of the instances where decimals are okay. The probability distribution of a discrete random variable lists the values and their probabilities, which is what we just built for our 3 coin tosses. And it's done most commonly with a table, like we saw. And again, satisfying 2 requirements. Every probability has to be between 0 and 1, and the sum of the probabilities has to be 1. Same probability rules apply as they did with our basic probability rules from the first half of Unit 4. Now, just another way to kind of take an example and build a probability distribution. Put all the letters of the alphabet in a hat. If you choose a consonant, I pay you $1. If you choose a vowel, I pay you $5. And so we're going to let X be the random variable representing the outcome of the experiment, create the distribution of X. Now, typically on an AP exam and on an exam for me, you have to define what are you calling X. We need to make sure that we're working in the same realm and we're looking at the same thing. So for this one, we want X to be the amount paid to you. Now, here you didn't pay anything to play, so we're not going to take into consideration what is actual profit. I'm just giving you $1 or $5 and hoping that you remember what a consonant is and what a vowel is. We're not going to consider Y in this instance. Our vowels are going to be A, E, I, O, U. So you have two possible amounts that you can be paid. You can either be paid $1 or you can be paid $5. Now, then we have to look at, okay, what's the probability of you winning each amount? The easier one to approach is vowels because we kind of know how many vowels there are right off the top of our head. Like I said, A, E, I, O, U. That's 5 out of the 26 letters of the alphabet. And that leaves us with 21 over 26 for the possibility of winning $1. And yes, it is as easy as that. It doesn't have to get overcomplicated. Again, this is one of those problems they throw at the beginning of an FRQ to get you warmed up and be like, yeah, I can do this. So I have my outcomes, I have my probabilities. This is my probability distribution for this example. And I briefly just wanted to touch on continuous variables. Continuous variables take on all possible values in an interval, and it's described by a density curve. What you are most familiar with is the normal curve, and we've done this many, 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 many times now. We've found z-scores, we've gotten p-values, any possible way that they would ask you about this on the AP exam, you have done. So we're not going to cover it again because we will kind of review for it before the exam. But basically, we're looking for that area under the curve, and the area under the curve equals to 1. All of it comes from those z-scores, those p-values, stuff we've covered. One thing to remember, you're dealing with discrete typically if you have a table or a histogram, continuous if you have a density curve. So let's go ahead and look at some features of discrete random variable. Something that they often like to ask is, if you were to do this event, what is your expected value? What do you expect to get? And that kind of equates to what is the mean of this probability distribution. So we have X is going to be the numerical outcome of a random event. We're going to define it depending on the context of the situation. And mu of X, or the mean, oftentimes, if they give it to you in symbols, in terms of probability, they will write E of X, which is our expected value of X when many trials are run. Remember, we are really focusing on probability being long-term behavior. We want to not see, okay, I flipped a coin 3 times and I got all heads. I must have a 100% chance of getting heads. We want to see, if I were to flip this coin millions of times, generally it's going to be a 50-50 split. That's why we focus on the long run. We don't have short run behavior. So to find the mean expected value of a discrete random variable x, we multiply each value by its probability and add all of the products together. So we have a formula for this. Formula is going to be, I'm going to take all of my x's, all of my possible outcomes. So I have 1, 2, xn, depending on how big I get. And I'm going to multiply that times the probability. So I did x1 times p1, x2 times p2, xn times pn, and then I add all of these values together, and that's going to give me my mean, or my expected value. I will say, generally in the wording of the question, they will ask expected value before they will ask for the mean of the probability distribution. And there is a compact formula. I believe this is the formula that they give you on your formula chart. Basically, it's the summation of same thing, your outcome times the probability of the outcome. So you're just adding up those multiplied values. So we're going to go ahead and do one of these together. Northwestern University posts the grade distribution for its courses online. Students in Statistics 101 in a recent semester received 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. Choose a Statistics 101 student at random. The student's grade on a 4-point scale with A is equal to 4 is a discrete random variable X with the probability distribution. So we know A is going to represent 4, therefore B is going to represent 3, C 2, D 1, F 0. So I'm just going to fill in my probability distribution table with those given percentages. Yes, we want to represent them as decimals just because it makes our life a little bit easier as we get into the multiplying. And now in words, we're going to state what does the probability of X being greater than or equal to 3 mean? And it's important because they will sometimes give you symbols and you kind of have to interpret it in context. So you want to make sure you know what exactly they're asking for. So if I want P is X is greater than or equal to 3, what's the probability of you earning a grade of B, because 3 is equivalent to B, or better? Or you could even say, what's the probability of earning an A or a B? Same thing. So I know I have to consider the probability of 3 and the probability of 4. So I'm going to take both of those probabilities, I'm going to add them together, and that's going to give me 0.68. So this is kind of just a general probability problem like our first example. And then we are asked to, in symbols, state the event the student got a grade worse than a C in terms of random variable X. So there are two ways to generally write these, whether you are using included or not. I think I chose to go the not included way. So student got a grade worse than a C. So worse than a C is a D or an F. So I did everything less than 2. An alternative way you could have written this is less than or equal to 1. That would still give us the same two outcomes to consider. So I have 0.10 plus 0.02, which is 0.12. And if this were a question on the test, I of course would accept both ways of writing the statement in symbols. If you wrote P of X is less than or equal to 1, it would be correct, as would X is less than 2. Just make sure you're using your equal to correctly so that you're getting the right way of saying what you want to say. Now we're going to compute the mean of the random variable X. So I'm going to go back to this formula up here. I'm going to take each outcome and multiply it times its probability. So 4 times 0.2x plus 3 times 0.42 plus 2 times 0.2 plus 1 times 0.1 plus 0 times 0.02. Going to write that out. Hopefully, there we go. So my outcomes, my probabilities, I plug this all into my calculator and I get 2.8. So what this 2.8 means, what the mean expected value is telling us, if I were to do this many, many times in the long run, we expect, and that's generally the language they want to see in your interpretation if you're asked to interpret an expected value. We expect a random student to get between a B and a C in the course. So take your numeric value, bring it back, give it context, and talk about how, in general, this is what we would expect to see based on this probability distribution. going to give you a little bit of time to copy this down, and then we'll move on to our last topic for today. And I will say, most likely, this is kind of what you will encounter in that beginning part of the FRQ. The end part we'll get to in our next couple of lessons, but a lot of the time they like to ask you, what's the probability distribution? What is the expected value? Two things they ask a lot. And there will always be at least one probability FRQ in your FRQ section. Okay, let's go ahead and head into, now that we've done expected value, we are going to look at our standard deviation. And something we have to consider is with standard deviation, we typically cannot calculate that straightforward with like just looking at the values. We do have to calculate something called the variance first. Variance is how much is our data actually differing from the mean. So notice I'm not only including my outcomes and my probabilities, but now I'm including my mu of x. So that's going to represent my expected value, or if you want to call it your mean. I'm taking my expected value and I'm looking at how far does my outcome differ from my expected value. And that's where we generally build our variance. This is going to be, of course, variance. This is going to be our standard deviation. So all we're going to do is take the variance value that we get and take the square root of it. Easy as that. They really will rarely ask about standard deviation, but sometimes they throw it in there along with expected value. It's not a big deal. It is something that takes a little bit more work if you were to work it out by hand, but we'll talk about how to do it in your calculator in just a second. We do get one of those nice summation formulas for this as well. Your outcome minus the mean squared times the probability. Then we add all of those together. Okay, so the daily lottery costs $1 to play. You pick a 3-digit number. We're looking at 000 to 999. If you win $500. Find the expected value of the lottery and the standard deviation. So the first thing we're going to do is define our variable x. X is going to be our winnings. Now, one thing you have to consider is the fact that this is a game that you paid for. So we're going to have to consider the possibility of us losing that $1. Even though we may win $500, we're still paying $1 to play. So I have two possible outcomes. I could lose, and that means I'm just out my whole dollar, or I could win and my profit is $499 because I paid my dollar. They gave it to me back. So with these digits, there's 1,000 of them. Only one number is going to win. So I know my probability of winning is 1 out of 1,000. Probability of losing, much higher, 999 out of 1,000. So in order to get my expected value, I'm just going to take my outcome, multiply it times my probability, add them together. So I get -1 times 999 over 1,000 plus 499 times 1 over 1,000. That gives me an expected value of -0.5. Now, it doesn't ask us to interpret this, but I am going to kind of give you a brief rundown of what this means. Basically, in the long run, if I were to play this over and over again, I would expect to lose 50 cents, which arguably means you probably shouldn't play the game because your chances in the long run are having a negative value. If it was a positive one, then yeah, sure, go for it. But anytime you get a negative, maybe you don't want to play it. So for my standard deviation, I'm going to first calculate my variance, my difference, my distance from my values to my mean. So I have my outcome -1 minus my mean -0.5 squared times that probability of getting -1 plus my second outcome, 499, minus my mean, -0.5 squared, times that probability, 1 over 1,000. If I plug that all into my calculator, I get 249.75. And with that, my standard deviation is going to be 15.8035. So I can expect to have my values typically vary from the mean by $15. So you may win 15, almost $16. You may lose almost 15, $16. That's kind of the distribution around it. Remember, our mean is our center. We add standard deviations as we go out. Now, this was already an intense formula for just two possible outcomes. It gets even crazier when you have 4, 5, 6. So there is a way we can do this in our calculator. You have done this in your calculator in some form before. We're just going to change some of the steps with how we input it. A pair of dice is rolled. Depending on the sum of the dots on both dice, Cole can win or lose money as shown in the following chart. Should Cole play the game? Explain your answer using statistics. Well, for this one, we don't necessarily know how much Cole paid, but they did tell us what the outcomes were, so we're just going to follow what they've said. He can win 6, lose 4, win 7, win 5, or lose 1. And what you can do, I believe, and if you missed something up here, I'll scroll back up at the end. I have my dice all set up. So I went ahead and looked through all of the sums, but I'm going to save you some time and give them to you. The probability of getting a 6, 8, or 9 is 14 out of 36. Getting a 2, 4, or 5 is 8 out of 36. A 10, 3 out of 36. A 3 or 12 is 3 out of 36, and a 7 or 11 is 8 out of 36. And all I did was go in and look at, okay, well, I want a 7 or 11. I got to go in and find where it adds up to 7, something like that. Now, with us wanting to see, should Cole play the game, I need to ask myself, is he going to win, and how much is he expected to win? So I want to know, is this something where, unlike with my game of the lottery, I had a negative expected value. Is this something that's going to give me a positive one? So what we're going to do is we're going to use our calculator to get this for us. This is still a small amount of numbers, but it is going to save you some time in the long run. So I have my calculator steps kind of written out. This is something we have done before. We're going to enter our X, our outcomes, into L1. We're going to enter our probabilities into L2. And then we're going to do one var stats, which we've done before. The only difference, every time we've done it before, I've said leave frequency list alone. You don't have any frequencies, don't bother with it. This time we do. We know the probability of getting each value. We know the occurrence. So I'm going to change frequency list to be L2, and you're going to get your mean or expected value. It can be either X bar or e to the X. They always come out as the same value. So don't have to worry about making a decision there. And standard deviation is our sigma X. So I'm going to go ahead and pull up my calculator really quickly. Let's see. I'll come back to the steps in just a second. I went to stat, edit. Oops, there we go. I have all of my outcomes in L1. I have all of my probabilities in L2. And the nice thing about our L2 list is I can go straight in and type 14 over 36, and it's going to change it to decimal form for me. So you don't have to worry about putting it in your main screen and then copying it over. Then I'm going to go to Stat again, over to Calc. I have one var stats as option 1. I have list as L1. I want to go to frequency list. So I'm going to just go down. And in order to enter L2, all you have to do is do second number 2. And L2 should populate. You see the little L2 above the 2 key? So L1, L2, and then we calculate. Again, if you don't have data in your table, it's going to give you an error. But if you have your data values typed in, you hit calculate, and then I get my expected value is 2.2222. Well, again, both of these will be the same. My standard deviation is 4.3596. So this saves you a lot of time and not having to use the formula by hand. So expected value is 2.22, which means yes, he should play because in the long run, he is expected to make $2.22. Now, that may not seem like a lot of money, but it's $2.22 he didn't start with. So anytime you end up in the green, meaning you haven't taken on a loss, it is something where you say, yeah, they can play. If anytime you are in the red, you have a loss of some sorts, you may want to consider not playing based on your expected value.